There we go. That's the reaction that this question is supposed to. You're like, whoa. There's a lot of words. There's a lot of thinking in this question. This question is going to be difficult just by how many words there are to begin with. So, and it's got an International Space Station, so it already sounds hard. So approximate model of the motion of an International Space Station is that it travels at a speed of 27,600 kilometers per hour in a circular orbit at an altitude of 400 kilometers. And we all know that the radius of the Earth, last time we measured, was 6,400 kilometers. Good. So let's draw a picture of this just to start with. We've got the Earth. Draw in blue because the Earth is mostly water. Maybe draw North America here, South America. Ooh, that's not quite South America. There we go. There's Florida. There we go. There's beautiful Earth. Very artistic. And up here we have our space station. They have like wings, don't they? That looks like a space station. Well, they fly. So now this space station is traveling in an orbit around here. If we went right from the center out, we know that this is 6,400 kilometers. And this little bit more is another 400 kilometers. So where it says visualize a line segment joining it to the Earth. Oh, look at this. This is perfect. Should be straight, but there we go. There's the line segment. And that line segment would be how long? 6,800 kilometers. We just have to add the 400 on to the 6,400. The reason that's important is now we can say we know that that space station is traveling in a circle, and that circle has a radius of 6,800 kilometers. To the nearest tenth of a radian, how much will it rotate in 40 minutes? How far will it have gone? How much will it rotate? Well, first of all, we need to know how far along here you would actually go. How do we calculate that? We know how fast it's going. Would it travel, if it's going 27,600 kilometers per hour, would it travel that amount more or less than that amount? It'll travel less, because that's how much it travels in an hour, and we're only going 40 minutes. It's going to be 2/3. Does it make sense that 40 minutes is equal to 2/3 of an hour, because there are 60 minutes in an hour? So if we take our 27,600 and multiply it by 2/3, we know that this has traveled 18,400. We could draw another big radius right there. What are we trying to figure out? How much has it traveled? Can we notice that this is an arc length question? We know the arc length. We know the radius. We want to find the angle. And we have a nice arc length formula. This formula on our formula sheet, which we simplified, that's the formula that only works if it's in radians. And since we want to find it in radians, we can plug in, we know that our arc length is 18,400. We want to find theta, our radius was 6,800. Divide both sides by 6,800. And we get 2.7. Use approximation signs because we rounded. 2.7 radians. That's how much it's traveled. To the nearest 100 kilometers, what is the straight line distance between the initial and the final position of the space station? So now we look back at our diagram, and we want to find out if this space station would have started here and just gone straight across to there to save time, be a little bit shorter. How far would that be? It's going to be a little bit less than 18,400. But how do we figure that out? Okay. We can't use our arc length formula right now because it's not going to be an arc length, right? We got a straight line. But if we take what we've drawn there with the red and the black lines, and I just draw it separate here. So this is part B. If I just draw it here, we had our black lines right here. We knew that our angle was 2.7 radians, and we want to find this, and those black lines were both those radiuses that were 6,800. Yes. So that's what we have. What's that? Is it an equilateral triangle? That's a good question. It would be an equilateral triangle if this was 60 degrees. Is 2.7 radians equal to 60 degrees? No. Is my diagram an accurate drawing? No, because 3.14 is like 180 degrees, right? 2.7, so it should be an even wider one. I should probably have drawn it like this with the 2.7. But we've just got a hypothetical drawing here. That actually doesn't matter how we draw it too much, other than the fact that this makes a triangle. Yes, we're going to have to use the cosine law. We can't use SOHCAHTOA. We can't use sine, cosine, tan, just regular, because this isn't a 90-degree triangle, but we could use our cosine law. It works with radians the same way as it works with degrees. So as long as your calculator's in radians and you type in radians, it will do all of those formulas that you've done in the past exactly the same and give you the same answer, which is really nice. So how does your cosine formula work? Well, if you want to find this, x, what did it look like? X squared would equal 6,800 squared plus 6,800 squared minus 2 times 6,800 times 6,800 times cos of 2.7. Should I write that out with letters again? A squared equals b squared plus c squared minus 2bc cos a. That was your cosine formula. Your cosine formula is not on your formula sheet this year. It will be on your formula sheet next year. Okay? So this year, I can't say for sure because I don't write the final exam, but I think there's an almost 0 to no % chance that they will ask you a cosine question on your exam because they haven't given you the formula. And therefore, people will do very poorly, and so they're not going to do that. But it is a good review because you will need to know this formula again for next year, so it's worth doing this question. So there's our formula. We notice in the formula that whatever angle we're trying to find, or whatever angle we know, is exactly opposite of the side that you're trying to find or the side that you know. And we can type this all into our calculator all at once, which is really nice. So my calculator is in radians. So I go 6,800 squared plus 6,800 squared minus 2 times 6,800 times 6,800 cos 2.7. So because we have all of those values, we can type all of those in all at once. My calculator's in radians. I can push enter. I get big number. We have to remember that that big number, 176088591. Did I miss a number? 0. Perfect. That's equal to x squared. So if I want to find out what x is, I'm going to have to square root my answer, 13269.8. Quick check. Is that less than it was originally? Yes. It's quite a bit less. Okay? Our diagram might actually be off because we figured, I drew the diagram, then we figured out the radians was 2.7. In reality, 2.7 radians would probably be more like this. Yeah. And if that satellite decided to travel directly, it might take out part of the Earth while going. So that might be a problem, especially if there's like mountains here. And it says to go to the nearest hundredth of a kilometer. So after we've written this, how would you round this to the nearest hundredth of a kilometer? So, well, that would be the nearest tenth of 10 kilometers. The nearest 100 kilometers, you're closer to 300 than you are to 200. I guess if you're traveling in space, what's another 31 kilometers if you're already going 13,000? Okay. Questions that are of similar reading length in your homework are 8 and 9.